Hi, I want to modify this equation now to show you a little bit more stuff what we can do with this. So the first thing I'm going to do here is modify the right hand side and have this be something different than 1. Let's do x here. And the thing I want to do here is break up this line. So now we will modify this code in order to get back this stuff here. So yeah, x. Great. Run this and see here that we have something that is cubic. All right. So this is now cubic, and how do we modify stuff in here? Well, if you go to our approximation, we have f here, and f is now x. So if we scroll down, f is now x. How do we fix it here? Well, we can't do it in an easy way. We need to actually go into this and modify it here. So f is now x, and x is, we need to modify it inside of this, for loop. So f is equal to x, so we need x first. So what is x? X is actually the interpolation of the coordinates inside of this function. So that's actually phi times the x coordinates. Here, this is x. So if you run this, we will have a problem here because this is there's a transpose here. So I'll get rid of this. So this is x. We have 2 Gauss points, and we have 2 x values for each of these Gauss points. So that's x. So now we can just say that, all right, f is equal to x. All right, because this is a scalar value, and then everything is fine. Or is it? Well, the problem with this now is this: if we substitute f by x here, and we substitute x by whatever we have here, and we see that we have phi times this phi here. So we have 2 quadratic equations multiplying each other. So this is actually power of 4 now, right? Because c is power of 2 inside there, and then c to the power of 2 times c to the power of 2 is c to the power of 4. So we cannot integrate this using Gauss order 2. We have to go one step up to Gauss order 3, otherwise we will have a small integration error on the right hand side. So now if we run this, just F5, we will see what happens. And there we go. And now, of course, this is one element, and we have one quadratic element in here. You can see that it's the curvature of this is quite coarse, so I will just increase this slightly. Let's do 20 points and F5. So one quadratic element now can't approximate this cubic equation quite well, so we just increase this to 4 elements. And we can first take a look at our L2 error. So this is 0.0385. all right, 0.30385. So go to n and increase this to 2. Run all. Scroll down here and see it. All right, we have a much nicer solution, and the L2 error is now 0.0048. So okay, so that's as easy as that. So nothing changes except inside here that our x has indeed. So we change f inside of this thing here. So what happens if we change things around here and do I don't know, maybe 2 times x? 2 times x. All right, so we do 2 times x here as well. 2 times x. So what happens with this 2? Well, this 2 propagates in here as well. So we can do f. I went too far. In fact, let me get rid of this stuff so I don't have to look at this all the time, and we'll actually not get rid of this. This might be useful. Let me just get rid of this then. Okay, so 2 times x. So 2 times x, and then we run this again. And we see that everything checks out again, and we have quite nice solution with a small L2 error. Okay, so what happens now if our order of integration is not right? What will happen to the solution? So we go back to 2. So 2, this is enough to integrate this correctly, but of course not this here. So what will happen? So we have a bad integration rule, and if you look at the L2 error, it has of course increased, but the solution still looks okay. So we can get away with this under integrating the right hand side. We can get away with this without losing too much stability, because it looks nice and everything. But what happens now if we indeed go down to integration order 1? What will happen then? We run this, and let's see what happened. Well, the matrix is singular to working precision, so this has completely ruined everything. We get not a number in here, we get inf, because our stiffness matrix is now singular. So we cannot do this stuff. It has to be integrated properly. The stiffness matrix here. So okay, go back to 1. I mean order. Go back to order 2. All right, so far so good. So this works well. Now what happens if we throw u in here? So we do, plus u. Okay, that means that we have plus ue in there, and then everything is kept the same, and then we do F5 to run this. So I just want to take a look at the solution, which is now something with e to the power of some x value. All right, so this means that we have, if I look at our approximation here, our weak form here, we have another matrix in here. In fact, plus a to b, we have u times v dx. This is what we have. All right, so this leads to in here. Can actually try to copy this. So we have uv in there, and then uv in there. All right, so for our approximation, we have, well, this, and then we have this thing becomes the integral from a to b, and then the approximation is this times v, which is here. No, that's bad. Go back. Like so, dx. Okay, and we break out u from here, so we have plus this matrix And let's get rid of u. Like so, and then we need to transpose this stuff. T. Alright, so this is the mass matrix. So this is what we have. And bold. Okay, so of course the mass matrix looks like there we have some, could have some value in here, and insert a space in there. Just get rid of this, like so, and times h. So this is the mass matrix. Oh, I already wrote it down there. Never mind. Okay, so this is the mass matrix. Now, of course, we need rho. Rho is equal to 1 because there's nothing in front of that u. It's just u. So rho is that, and then we can scroll down there. Right. So we can do ME is equal to SE. So just a bunch of zeros as well as ME. And then we do ME is equal to ME plus rho times phi of C transposed times phi of C times H times IV or IW. That's our mass matrix. And then we need to assemble this mass matrix. So we have M plus M, ME, and we need M to be equal to S. All right, now we need to add them together here. So S is equal to S plus M. So then I don't need to take care of it down here. And of course we can take a look at both S and M just for fun of it. So rho is not defined because it's actually defined up here, so I just do F5 to run all of the code and not miss something. So this is our stiffness matrix and this is our mass matrix. And then bam, we get a nice solution back here. Of course, this is just 2 elements. We need to increase number of elements to maybe 4. Run all of again. And bam, we get a nice solution back here that is quadratic, and the L2 error is quite low, and then if we increase it we will see that it goes down even further. So 0.024, you can actually copy it from here and just throw it in. I'm gonna get rid of this linear stuff. Gonna throw this in here and go back to take 8, run all, go down, copy the L2 error in here, and just call it a day. So I have what was the number of elements now? 8. So from 4 to 8, and I can get rid of this and run that. So I have a convergence rate of 3. So this is actually a cubic convergence rate for this type of problem. Okay, what happens if this is squared? Right, so this is squared. Well, we get something that is squared plus this stuff here. How do we take care of that? Well, f is now squared, right? So we just square this. So what happens now? We have something that is quadratic times itself again. So power of 6. Our Gauss order can only integrate until power of 5 in this case. So we need to go one order up to 3 and run. And this is our solution, and this is our error. And if you go down, I will actually copy this. This is for 8 elements. I will just throw this in here for this problem, and then run this again for n is equal to 4. Run. And take the L2 error for this problem, throw it in here and run this, and you can see that, yeah, it's close to cubic still. All right, so it appears that problems using quadratic approximations have a convergence rate of 3 here. So it's a cubic convergence rate, and we can modify our problems using a method like this here. So what happens if we change things up further? For example, the boundary conditions. So we can change the boundary conditions to be, to be something like du1 is 0, for instance. So that means that du of 1 is 0 here. So if we run this, we get something like this back. Okay, quite nice. Let's go down and change this. So that means if we have two bound, let me actually copy this from here. Oh, and let me get rid of now the weak form here. I will just keep the approximation actually. Because there's so much scrolling. Yeah, get rid of this. And also this. And this. I just want to have this. Oh, we have already derived this once. Right, so I will copy this to wherever I have my boundary conditions here. So what do I have now? So presc is what? Well, no node is prescribed, so we will just set this to empty, right? Because the solution is not prescribed anywhere. So this is just set to empty, and we can actually comment this out. This will actually do nothing. In fact, you can check it here. If we run this like so, and we do presc. All right, so the boundary conditions are both natural, so our prescribed nodes are non-existent, so they're just empty. So we set them to empty. We can get rid of this, just comment it out, and so G1 is now negative 0. This is this one here, so it's always negative, and then whatever value we throw in there. So in this case it's 0, and then G end, the last node, is -2. And this won't work now because, well, this is empty, so this will actually be a 0 vector, and all of this will be 0 vector. So we need to copy this boundary condition and get rid of this stuff over here. Now we can run this F5 and this should work nicely. So if we run this, get our true solution back here. So it works. Okay, so what we can do more is actually change this up and get rid of U here. So we get rid of that and we get rid of this. We can run this and unable to find explicit solution because we cannot have these types of boundary conditions if we have no U in here. Cannot exist. And the same thing goes for our solution down here. So if we have M here, and we can, you know, get rid of M here, run this, we get matrix close to singular or badly scaled. The results may be inaccurate. And this is because the determinant of S here is close to 0. So that's why it's completely wrong. Yeah. So that's why we need to have U in here. And if we have, you know, some other value here, 3 times U, I can have 3 plus 3 times UE in here, run this, get a nice solution, and can modify our problem. So that means rho is now 3, and modify M. We can add M to this back and run this, and we should get back our solution using 4 quadratic elements like this. So this works. You can play around with this. Now a note about this. If we change this to not be 0, to be something negative, -1 for instance, so -1, run this, and we get some sinusoidal thing back here. If we change the same boundary condition, so this is -1 now, and we throw in -1 here, so you keep this negative sign, it's supposed to be there. You can just insert your values in here and run this, and we get our solution like this. All right. So remember, you can always over integrate stuff, but you cannot under integrate. So if I change the order to 5 here, I will get back the right solution, no matter if this is too high order. I mean, there's no such thing. You can only under integrate. For instance, here, this we need a second order integration in order to integrate this correctly, because we can do it until order 5, polynomial order 5 with 2-point integration. So I can go down with 2, but the problem is that this f here is phi times phi times phi, so that's actually polynomial order 6, so this won't work, but it will be enough for the stiffness matrix and for the mass matrix. So if you take a look at our solution, we can see here that the L2 error is 0.0075, and if we go up 1, so 0.0075, and we take a look at this now. So this is, the right hand side is now accurately integrated, and we get a little bit of better solution there. Okay, so that's enough about this topic. See you later.